Hello and welcome to my YouTube channel. Today I am going to say on count data regression model. As far as the basic concept or background concept is required, we know that in many situations the dependent variable or the regressand is of count type, such as the number of visits to a doctor in a year, the number of accidents took place in a state or city per month, the number of car passing through a toll booth in a span of 10 minutes, number of suicides committed by farmers in a state per year, the number of patients coming to an emergency of a hospital within the time period 7 p.m. to 10 p.m. say for every day. Similarly, the number of patents received by a manufacturer firm in a nation, the number of prizes received by a student in a year, the number of times a player is injured during a year, etc. Sometimes count data also include rare or infrequent occurrences, such as getting hit by lightning in a span or a week, winning a lottery in 2 successive weeks, number of appointments to schools as a teacher made by central government, the number of alpha particles emitted per minute by a radioactive substance, etc. The underlying variable in each case is discrete, taking only a finite non-negative number of values. These are all examples of count outcomes or count data. A unique feature of all these examples is that they take a finite number of non-negative integer or count or values. In many cases, the count is 0 for several observations. Another important thing is that count example is measured over a certain finite time period, say per day, per hour, per minute, per month, per year, etc. To model such phenomena, we need a probability distribution that takes into account the unique features of count data. One such probability distribution is the Poisson probability distribution, and the regression model based on this distribution are known as Poisson regression model. An alternative to Poisson regression model is negative binomial regression model, which is based on the negative binomial probability distribution. Negative binomial random regression model is used to rectify some of the disadvantages of the Poisson regression model. So this is another way to estimate the count data. A unique feature of Poisson distribution is that the mean and variance of a Poisson distributed variable are the same. So this property is known as equidispersion. But in reality, if it is observed that the variance of the count variables is greater than its mean, then it is known as over-dispersion. Similarly, if the variance is less than its mean, then it is under-dispersion. Negative binomial regression model will be appropriate in this case. This video is based on the estimation of the Poisson probability distribution or Poisson regression model. Now we are concentrating on the Poisson probability distribution. If a discrete random variable, say y, follows the Poisson distribution, its probability distribution function is written as like this: function of y is the name of the variable, and yi, small yi, is the number of count data, is equals to the probability of that count variable is equals to expected value of minus lambda I into lambda I to the power yi divided by factorial y, where the function of y conditional on the values, different values of the count data, is the probability that the discrete random variable y takes non-negative integer values, that is yi. And E, we know E is more or less equal to 2.718 and yi equals to 0, 1, 2, 3 like this. And factorial y is like this, the formula of factorial y minus 1, y minus 2. And lambda is the parameter, that is the mean value of the Poisson distribution. In this video, we have used one example by taking the y, that is the count data variable, as the COVID death cases in last month in various nations of the world, and also assuming that this death depends on the level of development of the nation, the government's expenditure or spending on health as percentage of GDP, the number of physicians per million population, number of hospital beds per million population, people with age 65 and older, inequality of income, etc. Though the selection of the independent variable to some extent depends on the theoretical background, how these variables are related. So whenever you try to formulate the model, you must take care of the theoretical background behind the selection of the predictor variable. Hence, we can write the Poisson regression model as like this: lambda I equals to expected value of yi conditional on the values of the independent variables xi is equals to expected value of beta 1 plus beta 2 x1i plus beta 3 x3i plus beta 4 x4i equals to expected value of in matrix form bx, where xi are the explanatory variables that might determine the value of the regressand, and lambda I is the mean value for each individual. Therefore, we can write the probability of y equals to yi given the values of the predictor variables is equals to this, where yi equals to 0, 1, 2. Since this is non-linear regression, we have to apply the maximum likelihood method for estimation. After estimation, naturally we get the values of the coefficient, estimated value of the coefficient beta 1 hat, beta 2 hat, beta 3 hat and beta 4 hat. Now, the estimated value of the ith nation can be written as lambda I hat equals to expected value of beta hat x equals to expected value of beta hat 1i, beta 2 hat x2i, beta 3 hat x3i plus beta 4 hat x4i, in this way, taking log both sides, log of lambda hat I equals to this. So this is also known as log linear expression of the Poisson regression model. Now, if you want to estimate this in Stata software, the Stata command is like this: go to command section and write Poisson, Poisson, name of the dependent variable, then write name of the independent variable 1, independent variable 2, independent variable 3. If your model consists of 3 independent variables, then click OK. And your interpretation will be like this. After getting the estimated result, you can interpret in this way that regression coefficient as the predicted change in log counts, that is dependent variable, per unit increase of the independent variable. Similarly, you can also calculate IRR, that is incidence rate ratio, whose explanation is like odds ratio in logit model. The Stata command is just write in the same way as before: Poisson, name of the dependent variable, name of the independent variable 1, 2, 3, comma IRR. Here you have to just write this one in addition to this, comma IR, incidence rate ratio, and then click OK. The interpretation of IRR is like this: the estimated regression coefficients representing the multiplicative change in incidence rate per unit increase of the independent variable. For testing the goodness of fit of the model through deviance and Pearson's chi-square test, you have to write estate. Go to the command section and write ESTAT, estate GOF, goodness of fit. You will get the value. Now the most important thing is non-significance of these statistics. Deviance and Pearson's chi-square indicate that the model fits the data well. So the non-significance, remember, non-significance of the statistics implies the model fits the data well. For selecting the appropriate model, sometimes we take the help of AIC, Akai's information criteria, or Bayesian information criteria, BIC. That means the minimum is the best. Hence the command will be STAT, ESTATIC information criteria. As you know, the minimum is best, is better in the model for selection model. Similarly, another way to test the importance of each independent variable in the model, we can run the likelihood ratio test. How can you run this? First, you run the Poisson regression by incorporating all the independent variables in your model. Now you have to store this model. Then you have to drop any one independent variable. Now run by taking this reduced regression model. Then you have to compare through likelihood ratio test. Now the Stata command is like this. For estimating the complete model, you write Poisson, name of the dependent variable, name of the independent variable 1, independent variable 2, independent variable 3, enter. Now estimates store complete model. Your command is estimates store complete model. Complete model is the name given by you. You can use any name instead of complete model. Now your reduced model is like this: Poisson, dependent variable, independent variable 1, independent variable 2, and we have dropped the third independent variable. Okay, so there is no third independent variable. Independent variable 1, independent variable 2, enter. Then you have to compare with LR statistic. The command will be LR test complete model, enter. Don't write enter, just click enter. If it is significant, this implies dropped predictor variable is significant. Hence, we should not drop it. Otherwise, if the LR statistic is insignificant, it implies we can drop that variable. So this technique can be applied for other independent variables also. Now we are going to show the data set. So this is our data set. This is the name of various nations. This is the cases per million population, and this is the death per million population. This is HDI value, which shows the level of development. This value has to be converted in terms of numerical some ordinal value. 1, 2, 3, 4. 1 means the very high level of development, 2 means high level of development, 3 means medium level of development, and 4 means low level of development, as indicated in the Human Development Report. Now this is health expenditure as percentage of GDP is given. This is number of physicians per million population data. This is number of hospital bed per million population. Inequality of income, age 65 and older. These data you can get from World Development Indicators. Now you have to import the data. So file, import, Excel datasheet, browse, right here, the data is written. Browse, desktop, open, import first row. Okay, the data has been imported from Excel to Stata software. This is our data. Now go to statistics, go to count outcomes, go to Poisson regression, and give the name of the dependent variable, death per million population. Give the name of the independent variable. And one important thing is, whenever you use ordinal data or dummy variable, you have to put I dot before that variable, otherwise you will not get the separate result. Click OK. This is the result of Poisson regression. As we know, the estimated coefficient is the estimated change of log of counts with respect to change of 1 unit of the predictor variable. So from this result, it is clear that all variables are significant. That means for development variable, the all values are negative sign before the estimated value. That means that with 1 unit increase of the very poor nations, the death rate is less compared to the very high development or nations with very high level of development. Similarly, for medium development level nations also has less death rate compared to the very high. This implies the death does not depend on the level of development, rather the resistance power or immunity for the poorer nations, I think that is greater compared to the richer nations. That is why death rate is less compared to the rich or very high level of developed nation. Now coming to health expenditure, if this is positive, that means with the increases of 1 unit of government's health expenditure, the death rate is also increases. Similarly, the physician per million of population, the hospital bed per million of population, negative sign. That means with the increases of physician per million population, the death rate declines. Similarly, with the increases of hospital bed, death rate declines. The inequality is positive. With the increases of inequality, death rate also increases. This variable age 65 and older is also positive. That means with the increases of old age people, the estimated change of the log of the count variable is also increases. Now we are going to calculate the incidence rate ratio. Go to count outcome, Poisson regression. Here just you have to change report incidence rate ratio. You will get IRR. As you know, IRR interpretation will be same as odds ratio in the logit or profit model. So if it is 1 more or less, or 1, that means the 1 unit change of the predicted variable has no influence on the dependent variable. That means there is no relation between the two, independent or the predictor variable or the regressant or the dependent variable. Similarly, if it is greater than 1, that means there is an increment of the independent variable, the increases the IRR by a factor which is greater than 1, and hence the regression coefficient will also be positive. Similarly, if it is negative, it implies that with the increases of 1 unit of the predictor variable, the IRR is decreasing. That means decreasing by a factor which is less than 1, and hence our predictor hence our regression coefficient will be negative. So if we take the value, suppose this one, health expenditure, this means this is the IRR is 1.18. so if we subtract from 1, this is 0.1897, like this. It implies with the increases of 1 unit of health expenditure, the death rate increases by 18.97%. Similarly, if we subtract from this value from 1, it will be 0.01. This means with the increases of physician by 1 unit, death rate declines by 0.01, that means 1%. Similarly, for hospital bed also, with the increases of hospital bed per million, the death declines by 1%. So in this way, for inequality, though here it is shown that is significant, but since this is more or less 1, it implies inequality of income is not so much related with the death rate. And also the age 65 and older is more or less IRR is 1. Also we can interpret in this way also, that not so much related with age 65 and older and the death rate. Now we are going to show that the goodness of fit. As you know, you have to write a state goodness, GOF. So goodness of fit shows that the deviance statistic and the Pearson's goodness of fit statistic is significant, and we know the non-significance of this statistic implies the data fits the model well, but here it shows, our result shows that data does not fit the model well. Now it is also told that for calculating the AIC or BIC, that means Bayesian information criteria or Akaike's information criteria, we can show it in this way by writing a state IC. Okay, so this is helpful whenever we are going to select which model is better, because the less value of AIC and BIC reflects the better model. So sometimes we need to select which model we should accept. Model means how many predictor variables should be included, or which one should be deleted or dropped. Another way of doing this is the likelihood ratio test. Okay, so before running the likelihood ratio test, we have to run our full model or complete model once again. Okay, now we have to store it. That the command is estimates store the suppose complete model C. Okay, complete model. Now we have to regress the reduced model. Okay, we have to regress the reduced model. Now we are going to reduce the variable, suppose age variable, age 65 and older. We are reducing this and estimate. So in this estimation there is no variable, that means age 65 and older. Now we have to compare this model with the full model or complete model. How can we compare? You have to write LR test C. Okay, this result shows this is significant. That means if we drop that variable, so it is significantly affecting. That means we should not drop the variable. So in this way we can able to check which independent variable or predictor variable is important to include in the model, or not important, or we can exclude that variable. So with this I am concluding this video. So thank you friends. If you feel that this is helpful, kindly subscribe this. In my next video I am trying to prepare the negative binomial regression model, which is another way to estimate the count data, because when the mean and the variance are not equal, then we have to estimate. When the mean and variance are equal, then we can apply this technique, Poisson regression model. So thank you, that's all.